Hello. In this lecture, we will talk about materials. This is the outline we're going to cover today. Topics include nature materials, then we'll talk about the mechanical properties of materials. Then we're going to discuss three typical materials: metals, ceramics, and polymers. First, we look at the nature materials. We're going to start with atomic structure and elements, then look at how those atoms are actually bonded together, not only between the atoms but also between molecules. And then we're going to look at some typical crystalline structures and also non-crystalline structures. First, when we start to talk about materials, really we start from the very basic element of the material, which is atoms. When we look at the atoms, it's actually composed of a nucleus, including a proton and also neutron. And outside, you have orbits with electrons. So this is the what it's composed of. And there are if you look at this picture, then we can see some simple structures of atoms, right? From hydrogen to helium and also other elements. And so typically you have this nucleus in the middle, and then with different orbits, there will be different number of electrons. And so the connections between atoms actually is based on the forces between nucleus and also the electrons. And so there are two categories of bondings. One is the primary bonds, the other one is the secondary bonds. The primary bonds are typically the forces that form the molecules. For example, ionic bonding. Ionic bonding are those that atoms of one element that give up their outer electrons because it is not really stable, right? The outside, the outer orbit elements the electrons and outside of the orbit that is not very stable. Then they can easily lose those kind of electrons. And then one is losing, the other one is accepting. So this starts to form a certain bondings. And this kind of bonding is called ionic bonding. And another type of bonding is instead of one is giving up, the other one is accepting. Ionic covalent bonding is actually the electrons are shared between atoms. For example, this carbon and also hydrogen, right? They form the methane. So the carbon, and as you can see here, really its stable state is how many does it need? Right, 6, right? 6, and also we have 8, right? So the first one is first orbit, it should have 8 electrons, and then the second orbit, it should have 8 electrons. How can they form the 8 electrons? So because carbon already has 4 electrons, and if it is sharing with hydrogen with 1 electron, and then there are 4 hydrogen atoms, so it can start to form 8. Right, 8 electrons at the outside orbit. Then it become a very stable state for all the electrons and also atoms. So this is called a covalent bonding. And another type of the primary bonds is metallic bonding. So metallic bonding means the atoms are also sharing of electrons, but the electrons are actually shared among all the atoms instead of only 2, right? So typically for all the metals, they have metallic bondings, right? What it really does is all these electrons are actually forms a cloud, electron cloud. So electrons are moving here and there, and running here and there, and it's moving at a very fast speed. And this is why the metals have really good conductivity property, right? Because electrons move, so this is how it forms the current. And those primary bondings are really the forces how we can form the whole a molecule. Well, within a molecule, there are also forces between molecules, and we call it secondary bonding. And those are the intermolecule forces, not really transfer or sharing of electrons. So typically, secondary bondings, the forces between molecules are actually weaker than the primary bonds. And there are three forms of secondary bonding. One is hydrogen bonding. Hydrogen bonding means we have a positive side of the hydrogen with another atom's electrons. And look at here. So this is a hydrogen. And so typically, if you're going to have a hydrogen to be in a very stable state, it needs to have two electrons, right? So hydrogen already had one, and then if we assess another one, so we start to have a certain force, with with electron of another atom, and then this is how it forms the force between two of them. And also we have another hydrogen here, and it also can create certain forces or between electron and atom itself. So this is the hydrogen bonding. Well, another type of the bonding is the dipole forces. So the dipole forces is between two atoms between equal and positive electrical charges. And if you look at chloride here, it has a negative charge, right? And also hydrogen has a positive charge, and this electron also has a negative charge. So the positive charge of the atom of hydrogen, and also negative charge with the electron, and they start to form certain forces, right? So this is dipole forces. And also we have a London forces. So London forces is between two molecules. Typically that's because of the movement of the electrons. Because the electrons are moving at a really fast speed, so sometimes you will see a lot of electrons are actually of one atom molecule is actually forming a lot of electrons at one side. Well, at the other side, here there are not a lot of electrons. So in this case, with a lot of electrons here, we have a negative charge. With this side, without a lot of electrons, it has a positive charge. It starts to form certain forces, and that is called the London force. And London force, dipole force and hydrogen force, typically they are, a lot weaker than the primary bondings because they are really the forces, between the molecules. And when I say primary bonding and secondary bonding, does not mean they are, exclusive to each other. Instead, they all can exist at the same time. And here are some of the pictures. You can see the covalent bonding, with one oxygen and two hydrogen forms a water molecule. And if you have a comparison between these bondings, from ionic covalent bondings to metallic and secondary bonds like van der Waals forces, hydrogen forces, here you can see primary bondings, ionic covalent and metallic typically has really higher strengths, right? Higher strengths. Well, secondary bondings will have lower strengths. And same with the melting temperature. Because all these bondings are are very tight and very high strengths, so it's not easy to separate them, and that's why with higher temperature, primary bonds tends to have a higher melting temperature, while secondary bondings typically has lower melting temperature. And here are some examples of materials. And after we look at the one molecule, then let's look at, with a lot of atoms, what it's going to look like. So there are actually repetitive or patterns of structures can be formed by all these atoms. And usually it's the same structure, then we call it unit cell. It's the basic geometry grouping of atoms that is repeated, right? And if the collection of all these unit cells, then we call it, that is a lattice. And typically for all the metals, they have crystalline structures. And here are the three typical crystalline structures for common metals. One is the body center. The body center means in the very middle, and you can see this is with a cube. You can see one atom, and then also at all the corners it has one. Each corner has one atom as well. And all these, though, they can start to form a certain pattern, and then those patterns will repeat. And this is more vivid picture of the body-centered crystalline structure. When it repeats, right, you will see a more tight or packed structure, for these materials. And that typically body-centered cubic structures have a higher strength and also higher melting temperature. And some examples are chromium, iron, molybdenum, and also tungsten. As you can see, some of the materials are actually often used in making really hard tools. And another type of the crystalline structure is face-centered cubic. So face-centered cubic, as you can tell, here is all the atoms at each of the corner is actually formed around one atom in the center of the surface, right, like this. And here, if they repeat by itself, then it will start to form a more face-centered cubic structures. And of course, compared to body-centered cubic structure, as you can tell, they are not as tight as or packed as body-centered. So, but they are still, they still have very tight structure, and a lot of metals actually have this face-centered cubic. Aluminum, copper, gold, lead, silver, nickel, they all have this kind of a face-centered cubic structures. Something to note is that when you start to give a higher temperature of those materials, it actually start to change its crystalline structure. Maybe some of the material will be changed from face-centered to body-centered. And if you keep elevating the temperature, maybe it will change from body-centered back to face-centered. So at different temperatures, the structure, crystalline structure itself, it can be different. And this is why people invented some of the methods to manipulate the properties of iron, right? For heat treatment of iron, heat treatment of certain steels, it gives us a better properties of the tools. And that is by manipulating its crystalline structures with different temperatures. Well, another type of the crystalline structure is hexagonal closed pack. So this is the shape of hexagonal closed pack, and typical materials are magnesium, titanium, and also zinc. Of course, when not all crystalline structure have a really perfect pattern, really repeat itself. Sometimes you will see some defects. Defects can be a missing of one atom, or it can be missing a whole line of items, right? Or sometimes you will see missing a whole surface of the items, and this will be called as point defect, line defect, and also surface defect. And having all these defects will certainly affect its mechanical properties. You know, there are some of the mechanical and also chemical methods that you can actually put atoms, you know, on the materials or the surface to enhance its mechanical property. And in terms of the deformation in metallic crystals, and there are elastic and plastic strains. So elastic means the lattice structure can actually return to its original shape, while plastic strain means it's permanently deformed. Here you can see the elastic ones. After you remove the stress or remove the force, it can actually, you know, return back to its original shape. Well, after its plastic strain or deformation, you'll see there's already a slipped plane, which means that it has permanent damage or permanently deformed. So that's called plastic strain. And we talk about crystalline structures, which has you know, really regular repeating structures. There are also non-crystalline structures. Non-crystalline structures, they are actually less tightly packed, and also they are more of a random pattern. For example, air, right? Air has a non-crystalline structure, and fluid also has, you know, non-crystalline structures. Well, you know, if we you know, melt the temperature, say melt the crystalline structure materials, say the metal into a fluid state, which means that you destroy this crystalline structure into change it into a non-crystalline structure. But if you cool it down, when it becomes a solid again, it will change back to its crystalline structure. But in terms of which crystalline structure, it really depends on you know, the temperature it is, as well as how fast it cools down to the room temperature. And with non-crystalline structure and the crystalline structures, when they have different behaviors when they respond to the temperature. So when the temperature goes up, you can see the metal, it actually has a melting point. So the melting point is immediate change from its solid state to its liquid state. Well, if it's non-crystalline structure material, for example, glass, actually you can see this is the more of a slow change, right? Slow change of its volume. All right, after talk about the composition of the materials, now let's look at you know, material mechanical properties. What kind of mechanical properties are important in, you know, in applications? The first one is stress-strain relationships. So the stress means when there's a force, you know, we start to have a certain stress on the material, and those kind of stresses can be categorized into depending on direction of applying the force, and the stress can be categorized to tensile stress, which is to stretch the material, compressive stress, which is to squeeze the material, and also a shear it is to cause the adjacent portion of the material to slide against each other. So that is a shear stress. These are three types of stresses. And how to calculate the stress? So means that we use the force, applied force divided by cross-sectional area, right? So this is how we calculate the stress. You can see from this picture, right? We have this force, we have this, you know, cross-sectional area of A, and then we use F divided by A0, and we get the stress. Well, how to calculate the strain? So strain, basically, that's you know, the rate of change, right? Compared to its original length. For example, when we give you know, stretching this material tensile stress, and then originally its length is L0, and later after we, you know, apply this force, it is stretched to L, then the change of the length will be L minus L0 and divided by the original length. So L0. So here we get we can calculate the strain of the force. Well, when it comes to a graph, then we can actually map the stress strain when we're applying a force, right? When the force is constantly applied, and then you will, and also when the force increases as well, the stress will be different. And how does this the stress and strain are actually related? This is the graph. It shows that the typical material, that is how this responds to the external forces. Well, at the first period of time, it's actually the linear. It's a linear change, right? It's a linear change of the tensile strength, and this linear change is more of an elastic region, so which means that there's no permanent damage or permanent deformation yet. While when it reaches one point, which is the yield strength, what happens is that there will be a plastic deformation. So it means that there's permanent deformation. And starting from here, right, starting from the yield strength point, it will start to give more like this kind of a curve until it reaches a maximum load point. Right? Think of it as the case when you are trying to stretch a certain thing or material or part. At the very beginning, you need to really try really hard, and then you will reach a maximum load, right? So which is the maximum force you apply, and then you will see there the force you apply to stretch it is actually decreasing a little bit until it is the part of the material is actually fractured, right? So it follows this kind of a curve, and here at the point where there is a maximum load, we call this strength as a tensile strength, okay? And of course, later it will start to form this kind of a fracture point. When it reaches a fracture point, it means that the test is over, right? The test is over. We don't need to do any more analysis anymore. And so Hooke's law means it describes the relationship between stress and strain. And here we use E. E, it means Young's modulus, so which means that it's a modulus of elasticity. And to describe its relationship, we use stress divided by strain, we get E, right? Stress divided by strain, we get E. And this is its unit. So Young's modulus is really a measure of stiffness of the material. When we talk about stiffness versus a strength, right? Versus strength, what is the difference? So here we have a pair of chopsticks, and also we have a rubber band. Now in this case, certainly chopsticks have a higher stiffness because it's really hard to make it deform, right? It really deform, but it can easily get fractured, right? Compared to what? Compared to the rubber band, right? Think of how hard to make it a really permanent deformation for the rubber band. Really hard, right? Think of this way: if you drive a car, and drive on top of the rubber band, then probably rubber band will nothing happen. But if you have some chopsticks, and then you have to drive a car to go through the on top of it, and then pass the chopsticks, maybe it will fracture. So this is how to describe the stiffness versus strength, depending on which one has the permanent deformation. And Another type of property is the compression property, which means that we have a compression stress on the material, and this is the setup of the test. So which means that we have a base here or a plate or table, and then you put a test specimen, and then we'll start to apply a force from the top. And then when I keep applying the force, you will see the area, cross-sectional area is getting bigger, right? Getting bigger. So originally area is A0, now it's changed to A. So this is the compression test. Please watch this compression test setup video, so you have an idea of how it's conducted. There are also a lot of tensile tests for this one. It has a typical similar setup. The difference is the direction of applying the force. So for the tensile test, is applying the force to this direction. Compression test is actually squeezing it. Another type of property is hardness. So hardness means it's resistance to permanent indentation. So this is something we need to be very clear about. So in material science or in material engineering, when the hardness is really defined as resistance to permanent indentation, it's not talk about how hard the part is, right? Typically, when we say how hard the part is, that's probably talking about stiffness or talk about the strength. But the hardness here in material science is really resistance to permanent indentation. How easy, how hard to it's resistant to scratch or wear, right? So most of the tools, it should be made with very good hardness for scratch and also wear resistance. And how do we do the test of the hardness for materials? There are multiple ways of doing the test, but there are two common methods. One is Brenell, the other one is Rockwell, right? First, let's look at this Brenell hardness test. So for Brenell hardness test, for different methods, the really difference is the tip difference, right? For here, the indenter is a round shaped ball, right? Round shaped ball, and we can look at the Rockwell hardness test. The indenter is actually more of like diamond or cone shaped, right? A cone shaped indenter. And so this forms the difference of of indenting into the material. So when we are doing a test, what happens is first we start to apply a very light force on the material. So to make sure that the indenter is actually sit or firmly sit on the surface material. And then what it does is it will give another force to move the indenter a little bit higher depths, right? And then based on the force, based on the depth it moves, we can calculate, right? We can calculate a certain value, and this value is to describe the hardness, because higher hardness of the material surface on the material, it actually have the value we calculate will be different. Okay. So this is the equation to calculate the hardness with the Brenell method, and of course, you really don't need to remember this equation because mostly we're using the values, but you need to know how these are actually calculated. And for the Rockwell hardness test, it's also widely used, and you can tell the indenter is a cone shaped. It's pressed into the specimen. Similarly, first in initial position, we just let it sit on the material, and then we give a major force, which is to let it indent a bit more depth. Then we can calculate the value based on the force, based on the how long it travels with this indentation. Then we can calculate the value with Rockwell hardness. So Rockwell, Brenell, there's actually convergence but typically Rockwell is to test harder materials because the tip of the indenter is actually more sharp, right? So the Brenell is to test materials that's not as hard as Rockwell test materials. And here are some of the hardness values for some selected materials. You can see aluminum, lead, and also some steels and also titanium, and see how much the hardness difference it is. So when we are when we are buying materials or when we are designing some of the parts, we need to choose materials. Then we need to consider hardness, consider its strength, right? And also consider its temperature, how about how the material volume will respond to temperature. Another type of property is a fluid property, so which means that when some material in the room temperature is already at the fluid state, and also some materials that will be converted to or change the fluid state after it is melted, right? So dealing with those fluid properties, know how to calculate its flow and also stress strain of those, and then it can help us to analyze its the process. For example, metals are cast into melting state, and also glass can be formed to as heated and also fluid state, and the polymers same thing, right? Injection molding, typically we first need to melt the polymer and then inject it into certain molds. And viscosity is to describe the resistance to flow, right? Sometimes say, oh, that's very viscous. That means that it's really hard to flow. Sometimes it's not that viscous, means it's very easy to flow. So this viscosity. It measures the internal friction, right? And how do so this is the picture, as you can tell. How can we actually calculate what variables are involved in calculating the viscosity, right? All right, so after we talk about mechanical properties, now let's look at the three different types of common materials. The first one, the metals. Metal typically has some common characteristics. For example, its ductility, malleability, goes luster, and also high electrical and thermal conductivity, right? And typical starting point of the manufacturing process can be cast metal or raw metal or the powder shape, right? Powder shape can be, for example, metal 3D printing. Typically, are starting with the metal powders. And there are two categories or two major categories of metals. And if you are using some software or looking at some tables of the metals, you may notice that they put it as a ferrous and non-ferrous metals. So basically, it means does it have iron in it, right? If it has iron element in it, means that it's ferrous metal. If it does not, then that is non-ferrous metal. And here, as you can see, this is a typical some very common metals elements with their thermal property, a melting point, and also elasticity, right? The Young's modulus. And sometimes we may put two or more elements together into a metal, and then that is called alloy, right? So a metal that's composed of two or more elements, but at least one should be a metallic element. And So the solid solution for the alloys, sometimes you can see how it is actually composed. It can be, with the base, right? With the base material, for example, here is the copper, and but some atoms is actually replaced by the zinc atoms. So in this case, we can call it like solid solution with a substitutional solid solution. And also sometimes you may see some solid solutions are those that with a certain base and other atoms are actually filling the gaps right between those atoms. So this is called interstitial solid solution. For example, steel is like this, right? Typically, steel has certain carbon percentage in it. And if we have a copper as base and have a zinc, as integrating, and then it's called a brass. This is the composition of the brass. And for ferrous metals, there are two common alloys. One is steel, and the other one is cast iron. It really depends on how much the percentage of the carbon. If it's less than 2.14%, then that is steel. If it is bigger than 2.14%, but it's smaller than or less than 4%, then typically call it cast irons. And the starting point of the iron and the steel production typically are iron ores or some other raw materials, as you can see here. And when during the steel or iron production, typically the charge are the coke and also limestone. And here is a video to show how the steel is actually made. You should watch this video. And steel is a very common metal alloy in our life, and it's almost everywhere. And but steel is not just the iron and the carbon itself, and a lot of time it has other ingredients. And for example, manganese, chromium, nickel, molybdenum, and the reason that we want to put some other ingredients into the steel is because those elements or ingredients can actually help to improve the property of steel, right? For example, chromium. Chromium has a really good wear resistance property characteristics. Well, if we put some chromium into the steel, then the steel will also show some wear resistance. So that's typical non-wear steels, right? Or stainless steels, stainless steels. And molybdenum it's a really high strength material, and if we put molybdenum into the steel, and typically it will result into higher strength of the steel, and that's why we use molybdenum and into the steel for making some of the tool steels. Also, sometimes you may see other categories like plain carbon steel, low alloy steel, stainless steel, tool steel, and specialty steel. And typically that's really depends on what kind of ingredients they put in there. And next, cast iron. Cast iron has carbon content typically from 2 to 4%, and also silicon contents from 1 to 3%. And there are different types of the cast iron, like gray cast iron, ductile iron, white cast iron, or malleable iron. And for non-ferrous metals, these are all common metals. You have semaphore, aluminum, copper, magnesium, nickel, titanium, zinc, and also some alloys. We can go through in each one of them. Starting with aluminum. Aluminum in Europe, people really call it aluminium. It's the same, same material, and it has certain properties. For example, high electrical and also thermal conductivity, resistant to corrosion. Ductile metal. Also, aluminum is not very heavy. It's a light metal, so it can be used in a lot of applications, and it can be heat treated as well to higher strengths. And when airplane was just invented, originally it started with aluminum, right? Because it's light, and also it has good strengths. So aluminum has been actually very expensive metal in the past. That's because the production method of aluminum was went through a major revolution. But before that, aluminum used to be a very expensive metal that can be only be used in by those rich people, right? And for example, silvers can be made of aluminum. But later, after the mass production of aluminum, it gets more available to people, and then the price of aluminum has dropped. And now it has been very common material in our lives. And another material is magnesium. So magnesium is more soft and also lack of strength. So it's a light material, but it has really good strength to weight ratio. So the strength to weight ratio means with with the same amount of weight, it actually has a higher strength, right? For example, compare magnesium and aluminum, then you can see which strength to weight ratio is higher. If it's higher, it means we can use this property to design devices or design some components, especially for aerospace industry, because the higher weight of the material, it means that you need higher power, higher energy, and also it might cause some other issues. And that's why materials that typically with higher strength to weight ratio are better used in aerospace industry. Another example will be titanium. All right, copper and its alloys. Copper has a reddish, pink color. And here are a comparison between copper, brass, and also bronze. You can see copper has a little bit of reddish pink color, and copper has very good electroconductivity, and it has been used for wear, right, a lot, and it can be used in conductors, and also copper has this corrosion resistance as well. But its strength and hardness are relatively low. And typically, copper can be mixed with other ingredients to form bronze and also brass. It depends on what, for example, with zinc, it will form the brass. And nickel and its alloys, so nickel, because it has good corrosion resistance, so has been used a lot in coins. You will see, these are the different type of the coins used in our life, and also has higher temperature property, higher Young's modulus, so it has been a very good choice for making coins. We just mentioned a little bit about titanium. It has good strength to weight ratio, and it can be used in aerospace industry, but titanium also has some other properties, for example, biocompatibility, that they can be used as implants in people's bodies, right? And other properties of titanium will be has lower thermal expansion, so which means if you trying to melt it or increase its temperature, means it's more resistance compared to other metals that it to its volume change. And zinc has a lower melting point, but it has good corrosion protection. Galvanized steel is a type of steel that is coated with zinc. So some metals are with lower melting temperature, and with those lower melting temperature, they can be actually used in soldering applications. For example, lead and tin, right? Of course, lead element itself has some toxic features or toxic problems. So that's why in electrical components, the industry standard have been, or policies or laws have been passed to reduce the lead use in electronics material components. But lead and tin are really good material for melting, for soldering. And other materials are refractory materials. Typically they have really high melting temperature. They are very strong, very stiff, very dense. Examples are molybdenum, and also tungsten, right? Tungsten carbide. Sometimes you may hear that this kind of a tool it's very good candidate or material for tools, cutting tools. And of course, there are some of the precious metals as well, because of the availability, and also because of the industry itself. They typically have better look, and also higher price. And also all these materials are pretty stable, and we call it noble metals, because they do not easily interact or react to other materials. Then the next type of the materials will be ceramics. So the general properties of ceramics are they has higher hardness and also high stiffness. And it has good electrical and also thermal insulation. So that's why you see a lot of ceramics are being used in our food, right? And also in chemistry, because they are totally inert, and also they have high melting temperature. But ceramics are brittle and has no ductility. And ceramics typically have covalent and ionic bondings. Mostly, actually covalent bondings. That's why they form a stronger bonding compared to metals and polymers. And most ceramics have a crystalline structure, but it's more a little bit complex because it has more a mix of crystalline structures. Some ceramics can be more amorphous. For example, glass, right? Glass is type of ceramic. We already talked a bit about this, and so ceramics typically have a traditional ceramic and also new ceramics. But there's not really clear distinction between all of those. Traditional ceramics, typically you can see them silica or alumina, and also some like silica, right? We can use those to make our cooking wares, right? And alumina is a very common material for abrasives in grinding wheels. And some typical products will be the pottery, right? Tableware or can be made from those in China, stoneware, earthware, they're all common products. And also we can make bricks, right? Refractories, and also abrasives. And for the new ceramics, so the difference between the traditional and new ceramics is new ceramics are carefully or have a greater control during the process of making those materials. Because we can, have a better control of the process, then we have a better control of the structures, in the material, and this is how we can make even stronger or better properties of ceramics. And typically there are three categories of new ceramics: oxides, carbides, and the nitrides. So oxides, for example, alumina is type of the oxide, silicon oxide, and also alumina oxide is all typical oxide ceramics. And of course, they all have really high strength, good toughness, good hardness, low thermal conductivity, and good corrosion resistance. Some of the applications will be, like we mentioned, abrasives, and making brake or cutting tools or insulators. But also it can be used for bell ceramics, right? For example, artificial bones and teeth. And carbide, similar application, for cutting tools, and some metallic binders to fabricate some solid products. And also they all have really good hardness and wear resistance. Tungsten carbide, silicon carbide, titanium carbide, titanium carbide, these are all very common, carbide carbide materials. Another type will be nitride. So that's using, nitrogen as a base material, base element. Silicon nitride, boron nitride, and also titanium nitride. So they all have similar, applications. All right, now let's look at the last category of the material in this lecture is polymers. So when we talk about polymers, now let's look at this. The polymer, the word itself is composed of poly and mers. So which means that there are a lot of mers, right? A lot of mers, and each mer is actually a unit bonding between carbons and also hydrogen and other elements. So with one mer, right, we call it monomers. But with the polymers means that all these monomers are connected to each other, forming a long chain or a certain pattern, right? And so that's called the process of forming of the long chain and all a certain pattern. We call it polymerization, right? And so two ways of doing the polymerization. One is addition polymerization, so which means that each time we only add one monomer onto the chain, and another one is the step polymerization, so which means that you can with first start to form different smaller chains, and then smaller chains will be added together, connect together to be a longer chain, and this is called a step of polymerization. And we're talking about the polymers, really the material itself is not a lot of times we'll see this N means inside, for example, this nylon 66. And inside, this is the monomer, right? What is the unit pattern, right? And this is the mer. And we have n times of a repeated, right? Repeated pattern of this structure. Well, the n is really an average number, right? N is really an average number. It does not mean that every chain like that has the same same amount of repetition. So the molecular weight is actually the sum of the molecular weights of the mers in a molecule, and n times the molecular weight of each repeating unit. So n is more of an average number. And for the polymer structure itself, as you can see, some of the polymers, it has only a one linear chain. Some of the polymers, it may have branches. Some of the polymer material may have, they start to form this kind of net shape, or we call it cross-linked, right? Some of the cross-linked can be a little bit light, cross-linked, some of them can be really tightly cross-linked, and they all, for different properties, as we mentioned before, the mechanical properties and also chemical properties really depends on the structures, how they formed the materials, right? So thermal plastics, as you can tell, because it has a really simple chain or structure itself, it can easily be be reprocessed or returned to its linear chain shape. So which means that for some plastic or for some polymers, we typically call them thermoplastics. If we melt them, what happens is when we cool it back, it will change back to its solid state. So because all these chains can be actually formed back to its original shape, because they are pretty simple structure. Well, for other cross-linked structures, polymers, because they have really complex cross-linked structure, and when we melt it and break all these links and then cool it back together, cool it back to this original temperature, then it's pretty hard, it's really hard to return to its original shape or original pattern. So that's why you will see some polymers or some plastics, we typically call them thermal settings materials or elastomers. And what happens when we melt them is that they will start to burn. So this means materials are gone, and when you cool it back, it will not go back to its original shape or original structure. So that's the difference between the thermoplastics and also thermal setting plastic and elastomers. And that's probably why you notice that some plastics will burn, some of the plastics will just melt. And of course, with higher, more branches and more cross links, typically you form a stronger of the solid state material. And of course, more viscous if we melt, the plastic. And one term here is a degree of crystallinity, which means that how much crystalline structure it has for this material. Because typically for those polymer materials, some of them will have a crystalline structure, some of them will without. Well, when we talk about crystalline structure, we can see that with those repeated patterns, it actually starts to form very tight, right, structures. Those tight structures will give the material the performance is more like a metal, right? More like metal, for example, those ones, right? Because metals typically have crystalline structures. And depends on the degree of crystallinity, and you can see there are different polyethylene types, right? low density versus high density polyethylene, and they also give different properties. For example, specific gravity, Young's modulus, and also melting temperature will also be different depending on the degree of crystallinity. And the factors for crystallization, well, slow cooling will promote crystal formation and growing, and also mechanical deformation, right? It can also tends to align the structure and increase the crystallization. Sometimes we can use some chemicals to add it into the polymer to help reduce the reduce the crystallinity as well. And for the thermal behavior of the polymers, if the polymer has more crystalline structures, which means that we will behave more like metal, and you will see a clear melting point for from its solid state to the liquid state for some polymers. But if it is crystalline structure is not like a full, only partially like 50% of crystalline polymer, then it will be probably behave some between amorphous polymer and the crystalline structure or crystalline polymer. Thermoplastics, like I explained before, for thermoplastics, those certain polymers can be heated from the solid state to a viscous liquid and then cooled back down to solid, right? So this thermoplastic. Well, thermosets and elastomers, they can change chemically when heated. Crosslinks will be damaged, and will permanently fuse those polymers. They cannot go back to its solid state. And for thermoplastic polymers, and typically they have low Young's modulus and low tensile strength, and also lower hardness than metals and ceramics, but they are light, right? They can have a lot of good applications. So because they are, typically the weight is, not as high as metal and ceramics, they can be used in many industrial applications that does not require higher weight. Of course, they have lower, melting temperature, and it has good insulation property as well. And here's a comparison of a different common thermoplastics. And you can see their Young's modulus, melting temperature, and also tensile strength. And now let's look at some common thermoplastics. One is acetals, and this is one type of thermoplastic that is high stiffness and also good strength and toughness, and with good wear resistance. And that's why sometimes you may see those the plastic parts can be can be used to make some mechanical components, right, like gears. And acrylics is another common thermoplastic because it is transparent property. It can be used in making windows or making in a car, right? Car lights. And polycarbonate is a common materials used for injection molding. So it has many industrial products can be made out from the polycarbonate. ABS is another material that can be used in a lot of pipes and also fittings. ABS. Cellulose is a common thermoplastic. They can be used in textile industry as well. And fluoropolymers. So typically one is Teflon, right? We can see, some of the pans are made out of those materials because they have really good resistance to chemical and environmental attack, even with higher, temperature, with water or some other, liquids, it can still hold its own state. And polyamides is being used a lot in textile and carpets, apparel as well. Right, the common material will be the nylons. Right, and polyesters, PET, and the most time we hear is probably from the bottles, right? But it can also be used to make some other materials, and even those kind of PET materials can be reprocessed to make some of the textiles as well, clothes or shoes. I think Nike made some of the shoes that and then the materials are from recycled water bottles. Polyethylene, typically we have low density polyethylene and also higher density polyethylene. We just made that kind of comparison, and depends on the degree of the crystallinity, and you will see different properties of those polyethylenes, and also the application and the products will be different as well, from very hard materials, like those pipes, to to this kind of gloves, right? Plastic gloves. And polypropylene is another common thermoplastic for injection molding. Polystyrene, styrene foam is another common material that typically used for packaging. And PVC, it's a very common industrial material that is used for pipes, fittings, because they have really good property as hard, rigid, and unable to heat, and also light, right? Very stable material. And another two types of will be thermosetting polymers and also elastomers. You can go through the slides and look at what are the typical products they are. These are some common thermosetting polymers. And lastly, I need to pay attention and also remember these common polymer or plastic identification codes, from 1 to 7, because in our life, you will see this all the time, right? And from number 1 to number 7, number 1 is polyethylene PET, right? Number 2 is HDPE, number 3 is PVC, number 4 LDPE, number 5 polypropylene, number 6 polystyrene, and now number 7 is other polymers, which means it can be polycarbonate or can be some other polymer that, or ABC, that not named from 1 to 6. I want to talk a little bit about polymer recycling and about degradability, because polymer recycling has been very difficult. It's, for one reason, is it does not have a really mature business model for recycling polymer. Yes, a lot of polymer can be recycled, but the process is very expensive, and it does not make a very good business case. And that's why there's not a business doing this. Another difficulty or challenge is that when we are using recycled polymers, typically the quality of the polymer or the reprocessed polymer is not comparable to the virgin material of the polymer, and especially the the raw material for making polymer products is actually from the gasoline, and and the cost of making virgin polymers is a lot lower than reprocessed polymers. So that's why it causes a lot of challenges in polymer recycling. Some of the polymers can be biodegraded, but it still, it takes quite a long time. Typically, for polymers like PET, all those, it might take hundreds of years, at least 100 years to degrade in the land. Think about how we can reduce the use of polymers, or I was thinking of the ways how can we reprocess the polymers so they can enter into another life cycle of the product. All right, so that's all for this lecture about materials.